Hello.
Go for it. Greetings.
Okay, sounds good. Hello, welcome to the talk for the reverse engineering TRS-80 Model 1. I'm Marcel. I have everything what I've created on my GitHub, so everything is free. All the STLs, all the files, everything I will talk about is available free on my GitHub. You can follow along on my Patreon, which is free to join, and I use it as a blog there. So what we talk about is, if you don't know me, I have reverse engineered pretty much all the Model 1s, all the different revisions, the case, and so on. And yeah, I want to talk a little bit about the journey, about how I've been doing that. The majority of the time we probably will be spending on the PCB itself, but there are also other topics like reproducing individual parts and redesigning, creating new extensions, and so on. So first was PCB. The best thing is to start with the schematics. If you haven't seen this technical manual, this is actually a really good manual which talks about how the Model 1 actually works. It doesn't go into detail in some areas, but generally you get a good overview of how things work. And it has a neat schematics at the end on 2 pages, each 4 pages long. It's quite a bit of a mess trying to understand this. And so first thing was understanding this schematic and replicating it. And so to first understand it, I wanted to break down how the Model 1 works in graphical terms. And so I came up with this graph on the first page, separating specific features on individual parts of the Model 1. So you can see on the left-hand side the Model 1, and on the right the schematics. The blue area is the power. Then you have the red area is some test features they had to test the Model 1 in the factory. It's not used really doing normal execution. We have the clock, the CPU, and these are all the buffers around the CPU, supporting all the glue logic around the CPU, for example, for the reset button and so on. Then there's let me see what it is. It's the CPU gating. This is a buffer area. Everything is buffered on the Model 1. So if the CPU wants to talk to any component, it needs to go through these buffers. You can see it also there. Everything has to go through these buffers. And that's because the CPU is a CMOS and not a TTL, and it can't drive as much of the logic as it needs to, because it's a whole bus. And then there's the address selection. Then we have the ROM. Sorry, the screen is very small here on my side. Okay, let me try. So it's the RAM. Then we have, sorry, I can't see it here. Let me change this. Okay, where's my mouse? Is it on the bottom? Is it on the left? Oh, there you go. Sorry, I have to mirror it. Okay, I hope this is better. Yes. Okay, so that's the cassette interface. And then we have the video section, which is actually quite large. There are actually 2 parts of this. One is the CPU section, and one is the video section. It's about half of the board is video that runs independently, and it will actually keep generating the video, while the other part is the CPU. And then we have the edge connector. So overall, this is the full system from a high-level view. Now we've created this schematic, and you can now dive into specific things, for example, into the CPU. You can see all the components related to the CPU, or you can go into the video section. And there you can dive into deeper things like the video counter, the video access multiplexer, and that's where the Z80 injects. So generally what the execution is, it's going from left to right. So it goes to the counter and all these components until all the way to the right, where it goes out as a video. The Z80 interjects here in this part and can now access the video RAM, the static RAM. With that, it can write anything into the video RAM, and then it gets it also back if it wants to read something out of it. This is the only place where this can happen. And when you actually do this, when the CPU is accessing it, you get these snow on the Model 1. Other than that, it just keeps on running and generating. It's, again, two independent systems, and this is the only place where they sync. So here you can, again, dive deeper now into the video section, and you can see the schematics are now broken out into 21 pages. So I tried to categorize them to make a little bit more sense than having this overall schematic. But this was, for me, actually just to understand the machine. That was the initial purpose for me to dive into this. But then I found so many issues on the schematics, so much so that some of these just did not make sense at all. So I wanted to do more, and I wanted to dive deeper into this. And so the next thing I wanted to do is get a board and look where all the trace is going. So these are a couple of boards I bought. These are different revisions I bought to see the differences between all of them. And so I cleaned them up and then started to desoldering everything. Because a lot of these traces going under the ICs, and I wanted to make sure I really know where they're going. I can check these, but I also wanted to create a one-to-one replica so that every trace looks exactly the same like the original, everything goes the same way. So I did all of this for this revision G in this case. And this one is actually a picture of a revision E. And so I put it on the scanner, scanned it in, stitched it together because my scanner is not that big, and created these two layers. Now I was able to import these into my electronics app, which is KiCad. I use an open source KiCad. And then I can start getting the frame. So cutting out the board, making sure it's exactly the same size like the original, because I can now overlay it in the background and I can see where everything is. I can also make the right holes to make sure it fits into the case, because if this is a millimeter or two off, it just won't fit. You now have to strain it, and it's not really great. And the problem is you can't actually move it so much, because when you look at the holes, traces are getting very close. And I actually managed to make the holes slightly bigger to give me a little bit more room, but there was not much space to do that. So now I had this. Now I needed to get all of the silk screens. For every component, I created my own footprint with my own silk screens and made sure that they look exactly the same as the original. And you can see there are different things, like even capacitors have different types. We have the CR2, which is a diode, and the resistor right below it. And then we have also the ICs. And you can see on the ICs there's something interesting. It doesn't have pads on all of the pins. And that's because you can see here in the bottom, I can't point with my finger there, but in the bottom center, Z44, there are some connections being made past the pads, and they have to be actually thinned out, because the risk of having a pad there could be that there would be some bridging during the manufacturing process. And that seemed to be actually have happened. Last year I talked to Steve, and that was the major issue there in production. And so they removed all the pads on the front where it wasn't actually needed. And this is across the board. So you can see here another example of this, where here they forgot actually one pad where it didn't need it, but it still had it there. But on my replica, this is a picture of my replica, I actually replicated that too. Nowadays, we don't really need to do this anymore. I just wanted, again, to get it as close as possible. So you can see that there is the solder mask, but no pads. And yeah, so when I had now all this board, I could set up the zones here, the fill zones for 5 volts and whatever, and then trace all of the traces one by one. So you see it's a little bit off, and that's because my scanner has a little lip around it. So there's a little change, and so I actually printed it out and made sure that it is on a foil and overlaid it to make sure it's exactly. So it's a little off here, but in actuality it's actually on top of each other. And so I did the same for the backside. Luckily, that's only two layers, so it was reasonable to do. And so if you combine it, that's how it looks like. The next problem was making sense of it, because, as I said, the schematics sometimes didn't make sense. And so what KiCad, the program I use, does is it makes sure that whatever you define in the schematics, you can't actually make a connection on the physical board. It will not let you. And so I needed to, when I tried to do the traces, it didn't let me. And so I knew, okay, something is wrong. The board says this, schematic says something else. And so I had to reconcile this now. And you can see all of these lines are the connections you have to make. And so for all of these connections, I needed to double check if they're going into the right places. And so here you can see that some on the left-hand side, you can see there are some of the traces are not complete. And then on the right-hand side, I have to move things around because they used the wrong IC or something like this. And so I moved this all around until all of this worked. With that, I had a full board. I produced it, and yeah, it was working. Until I found some differences again. So you can see the top is the follow-up. The first one in the bottom is the first version, my revision A for that. Yeah, I needed to make that change. And so I went from A to all the way to C now. So I always found some small issues, and I made some improvements. Electrically, they're all the same. It's just some minor cosmetic thing, actually. And so I went on and did it for all revisions out there. So revision A, D, E, and G, that's all I know. I tried to get various ones. I even got one from Ian. He sent me the E one because it seems like it's very hard to get around here. So did all again for all of them. Yeah, and moving all of the traces and so on, because most of the traces are the same, but there were some differences, and so I had to go and rechange some things there. An afternoon. Yeah, it's I have a high-accuracy desoldering gun. With other methods, it would be taking a lot longer. Yeah. So some of the differences. Some of the interesting surprises I found. First is, there are 2 C58s. One right next to the ROM and one next to the relay for the cassette. I guess they forgot that they had already a C58, and they just added another C58. I always get questions, oh, where's this C58? It's like, okay, that's this one. The next thing is, they swapped sometimes the reference designator. In revision A, they had it on the left-hand side. In later revisions, it's there. Can you spot it? So if you're trying to debug something from some technical manual and they're saying C20 and then you're going the wrong one the whole time, that drives you crazy. Other things I found is some dangling logic, which was floating. It was unconnected in revision D and E. I think that these were some tries for revision G, actually. And revision G, they were actually used. There are also a new resistor, R67, which was 100 ohms, but on the board it was 220 ohms. Also, in the schematics, they defined it as a quarter watt, but on the board it's a half watt. And it has also an R67 somewhere else. So another time when they did double reference designators. So again, that makes it all a little bit more difficult. So to talk about some of the features, I need to quickly go over the video sync section, which is actually the one which breaks all the time, so it's probably very useful for you to learn a little bit about it. So there's the vertical section. You can see it's highlighted on the left-hand side. And then you have the horizontal section. And then there's one which combines the horizontal and vertical sync into one. And these uses CMOS. These are the only areas which use CMOS ICs. And as far as I understand, and this is some of the analog, which I'm not too familiar with, but Matt actually gave me a hint that this is some kind of strengthening it. Yeah. Anyways. Oops. So in revision A, you can see that some of the capacitors and so on are on the top, while they moved it a little bit down in the later revisions. And the reason for this is the whole section looks a little bit different. It didn't use all of the ICs. Most of the inverters in the bottom IC wasn't actually used, but they fixed this in later revisions. Another change is the additional C58 in the cassette interface for the remote. This is so that the relay doesn't actually lock up, and because every time it closes, it could spark, and then it could shut. And so they use these diodes to make sure of it, and there's also a capacitor, which is actually never filled. I haven't seen any board which actually has the C58, the additional C58 actually used. Next step is the actual test signal. I know that a lot of people are not actually familiar with the test signal, but the test signal was used to unhook the CPU from the rest of the system. So on the edge connector, it has this test signal, which goes out from the card edge interface all the way over to the CPU. Within the CPU, it goes to the bus request, and this is to ask the CPU, finish your work, I want to take over the bus system. So with that, the CPU can stop doing anything on the bus and can let a different system do its thing, right? In other systems, you see it as a DMA, direct memory access, but in this case, it's just accessing. It was done to test the machine after it was produced in the factory. And that's why it's called a test signal. That's why it's named test. This is working great, and it also goes into the dB in, dB out. It makes sure that everything is only read. So it actually doesn't write anything out. It doesn't drive the bus. And so it goes to the gating too, and here it removes the connection to the address bus and control signals. So it disconnects the CPU completely from the system. So everything goes to the address bus, and the data bus goes through this, and so as soon as test signal is triggered, there's no more connection outward. The problem is in revision A, this doesn't work because they forgot to make the connection. With that, you can actually destroy your revision A because it will still keep driving the bus, and so the ICs will have contention, and over some period of time, you can actually break these ICs. An interesting thing is if you ever start your Model 1 and you can't get it moving, it shows garbage. It's most likely one of these buffers are broken. That's because the CPU can't now access anything on the system. Some other more interesting things is there are two R28. The left-hand side is actually an R26, but I looked at it. It's an actual 8 printed there. It's not a 6. In revision A, they had a specific arrangement. In later revisions, they rearranged things. Again, if you don't pay attention, you might actually mess up. There are also some interesting things is where they moved a capacitor in one revision, but they forgot to move also the silk screen. So the silk screen is left in the old place. And as I mentioned, on the top they had some pads missing. In the bottom, they had only these 3. All the other pads are there. And the reason for this is they needed to get this trace there, and it was just too close. And so we removed that. In my replica, I actually replicated this in revision A. I stopped doing it because I got a lot of questions, because it's really hard to solder this because now you have to solder it from the top when you have already an IC in it. So that's, and in revision B, I just put them back to make it a little easier, because nowadays we don't really need that anymore. This one is one of the most significant changes. In all revisions before G, the clock is very different. So with the help of Mike Gore, I captured all of the signals and actually figured out what these signals are. And when you look at the revision D and revision G, you can see there is some shift to the right. So what it does, it just moves it into a later point. And the reason for this is the DRAM got faster, and with that, it caused some issues because they need to be following a specific spec, and they just used, they didn't really follow the spec there in the earlier revisions. They also need to make this change, and the reason for this is otherwise the signal would be now too short. So if you go back here, you can see on the right-hand side how small the CAS signal is now. It was just too short. And so they had to make these changes, so it's now fixed on the left-hand side. They also fixed the refresh. Before revision G, the DRAM refresh also triggered a CAS, which is not actually needed for a refresh. You only need a RAS for a refresh. So here again, they followed, fixed that. Let me see what the time it is. Okay. So you're probably all familiar with the Z3 address configuration. And so this is just for the address mapping. Here you can see how this is done from the top to the bottom. And you can see 0 with a hex 0, starting an address with hex 0. And here's a binary version of that. Can be mapped to ROM A, hex 1 to ROM A2, and then you can map things to B. So with this, depending on what pin what connection you make, you can now rearrange the address space in your Model 1. And that's what you have to do. Depending on what ROMs you have, if you have, for example, this level 2 board at the end, you actually have to set the first one because it has a central one. You also have to set all the others to make this work, because you need to get all of these connections made to control this board. So the top bit was actually done just for the level 2. And then you have also the DRAM address mapping. The interesting thing is, in revision D, the 4 address is always set. You can see also that there is no level 2 a jumper there. They had to make some other changes, get the data from some different place. And revision A had also always a connection, but you can see that 4 was always connected. While here you can actually set the connection in revision D, but it doesn't even make sense. Also, revision A has only the 7 bits. All the others have 8. So if you look into the case, the edge connector, and you can see a DIP which has only 7 bits, you already know it's a revision A. Z71, often people think that's also part of this address thing, but it's actually only for the DRAM configuration. What kind of DRAM do you have? So you can have 60K, you can have 4K, or anything from beyond A can also support 8K. And there are actually 2 different versions depending on what DRAM you have. And again, revision A has only 7 bits. It doesn't actually use this, and it doesn't support 8K. There are also some differences. They turned off the 5 volts on the edge connector, and so a lot of people actually patched this up in their revision D and earlier. Revision E has that too. In revision G, it was actually finally fixed. And the reason for this is that some of the peripherals use the 5 volts to drive their electronics, but that also caused the Model 1 to crash, and so that's why they disconnected this so that it doesn't happen anymore. So if you look at the revision A and revision D, there are some changes. Not a lot, but a couple of changes. Revision D and E is pretty much the same, and revision G is quite different again. Again, this is only the one side. So I made a list of all the differences, and then there were the Japanese revisions. So I thought I had 4 revisions, great, nearly done. And I did all of this again, and I realized there are 5 revisions, 10, 20, 30, 40, and 50. I've done only 2 right now. I have 2 more boards at home to do. I'm still looking for 40, so if somebody has a 40 board, let me know. The interesting thing is also everything is curved. It's not in an angle, except some of them. This is the backside. Another thing is, and you can see because everything is curved, they did it by hand at Tech. So they also did the silk screen by hand. So every silk screen, every resistor, everything was different. And so I had to replicate for all of them. That took me quite a bit. I think just 2 weeks just painting, tracing all of these. But yeah, finally I got the schematics also correct there. So on the right-hand side, you can see the Tech version, the Japanese version, and it's slightly different. I think the biggest difference is the cassette interface now supports changing the character generator. You can actually connect it to the I/O. You can set a basic command, and now you have a different character generator. Another thing is the keyboard is now behind some buffers. Previously, it was directly on the data bus, which caused some issues. So, for example, if you disconnected the keyboard, it just keeps on blinking because it thinks some buttons are pressed. And the keyboard doesn't actually work on the Model 1. It has a different, different pins connected. So you can't actually connect a Japanese Model 1 keyboard to a Tandy Model 1 keyboard. To make it work, I also created an adapter. Again, it's on GitHub. So if you have a Model 1 keyboard and a Japanese board, do you want to connect that keyboard to the Japanese Model 1? That's a way to do that. Or if you have like a modern version of the keyboard. Another thing is it finally also supports PAL. With that switch, you can switch between NTSC and PAL. NTSC is the left-hand side, the Z5B. The connection made up is NTSC, while the connection down is the additional logic for PAL. And this is actually within the counters. When the rows are counted for the video, it has a different point when it resets this counter. And so that's what that is. Japanese version also has now 8 bits of video RAM. You don't have to do a lowercase mod. It already has 2 chips, each with 4 bits. The video section is completely new. It doesn't have any more the CMOS in the vertical sync or the horizontal sync. Unfortunately, still in the combining of the sync areas. If you look at the Japanese board, you will probably see baud wires. These baud wires are factory made. The reason for this is they built these boards and then realized some issues, and then they scratched some traces and made the baud wires in the factory. I haven't seen this with Tandy at all, but I guess that's why there's only A, D, E. Probably the ones in between had these issues, and then they skipped to the next version. But Tech just pushed these out anyways and fixed them with baud wires. And so you can see on the right-hand side the traces they cut. I wanted to do that too, and so I cut the traces already on the board. I could have left them in and asked people to scratch them, but the problem is, if I do that, you can see that like this one IC drives the other IC output. So both outputs together, and this will break an IC. So I didn't want that, so I already pre-scratched it. There are also some other things where the ground wasn't connected, and so they had to botch wire the ground connection. Or here they had to cut the ground connection. There is a small cut here. And this was because it introduced some issues with the DRAM. So in later revisions, as you can see here, it's gone. So this is the revision 20. Revision 50, they added a lot more fills. Okay, that was the PCB. Let's see, I have some bit more time. The next problem was component sourcing, right? Some of these components are really hard to get. For example, this relay. It's a very interesting shape. The switches, this was the hardest to find, surprisingly, because there are these self-locking. It was very difficult. The reset button was easy. The power button was pretty difficult for me to find. And then also the power transistor. But everything else was actually quite easy to get. Except some of the custom ones. The left-hand side is the character generator, and on the right-hand side are the ROMs. These are custom-made for this machine, and yeah, it's really hard to get them nowadays. They're often donors. So what I did is I created some adapters for these to make sure I can build my own, and use a normal ROM. And here I can actually, I put 32 on this because there's so much space, so why not fill it up with characters. And here I also made it possible to flick specific features on. So for example, in the first version of the character generator, they had a floating A. There was a lowercase a floating. They couldn't see it anyways because there was no lowercase mod, so they left it in. As soon as there was a lowercase mod, they brought out a new version which had that fixed. And so you can switch these individual features on, all the different versions that are out there. You can test these out. For the system ROM, similarly, but I wanted to make sure that it's custom enough so I can use any ROMs and on any machine which use a similar one. And again, connected them so that you can select one of these ROMs. Again, put multiple ROMs on it to be able to switch this. Now, I had all of these different machines. I created replicas for all of the revisions. So now I had like 8 machines at home, but no case. So I made a case for this. So I designed a case that looks exactly like it. If you print it, you can actually use the top on the old one, for example. So they fit into each other. And this is the case you can print. This is a resin printed case. And so that's the result of that. But then I also did the bezel for the keyboard. And so spraying it, it looks very close to the original. I would say even the same. The paint doesn't look the same. So I went and tested all the different paint colors. When I thought I had one, I went inside and it was a different color again. That's because how the light works, right? So it's really hard to find the right color. I think it's close enough for me that I was happy with that. And then I also replicated all the other parts because why not, right? I've been already on it, so why not all the parts? And these are just a small selection of it. I have all of them on my GitHub, so you can print all of these. I also wanted to then fix a keyboard. So this one is a metal shield for the keyboard. You can see the original and my replica for it. Again, everything is open source there. Required a lot of testing, a lot of different things. I tried to do it printing, but it bends too much. So I have to use a metal shield, which is unfortunate because it's somewhat expensive. Then, since I have now an Alps keyboard, you can see that on the left-hand side, it has now my shield. It has my PCB, because I also replicated that PCB. But the switches you can't replicate. Okay, you can, but it's probably not worthwhile. You can still buy them, again, but they are very expensive. Some are like $5 per switch, and if you have to have like 65 of them, it's getting really expensive. And so I created a replica MX keyboard, a modern MX keyboard, again with shield and everything. I needed to make some modifications. You can see here's the standoff for the LED for the keyboard, to make sure it's the right distance for the LED to show up in the bezel. And while I was doing it, I also realized there are so many different manufacturers with different sizes of spaces. And so I had to make a custom footprint to make sure that I can slide them left and right to make sure that they fit. I also wanted to not just use any kind of keycaps off the shelf. So I made my own template and produced keycaps so that they look exactly like the original. You can see also there are a couple of more buttons, and that's because I worked with Jay Crudy to also support the Model 3 and Model 4 keycaps, so that all of this is in one. And with that, I had a full keyboard. I also did a power supply. This was the first design I found. And so this one was actually not my design, but I created the PCB and the case. I wanted to have like the fuse outside. And so I created this one, but it's really big and heavy. And then I found Matt Boytum's design and rearranged it a little bit so I fit into this case, because again, I wanted to have this kind of switch in it with a fuse accessible from the outside. So that's now much nicer. But there are now actually even nicer and smaller ones out there on eBay, which Dusty actually produces, which is actually really nice. Then I also started with the monitor. I finally got myself a 3D scanner, because before I used all calipers and so on to get the case correct. Unfortunately, you can see there's a lot of bumps and not really nice. But it was useful to get all the measurements right. And so I created a replica of the monitor. But now, what about the CRT? Yeah, CRT is not really great, because where do you get the CRT from? And so I created an LCD version, which is 65% of the size, and it's on my table, and actually over there one. And this has all of the modern components. It has the buttons on the back, so you can switch it, but it works like the Model 1 monitor. It looks like the Model 1 monitor, but you can use it for anything. So here's how it actually looks like at the end. I also got from Matt this Archer speaker, which also replicated. Here's my prototype. You can see that they're still hot glued everything in, because I did a mistake. But here you can see it's now the final version, which has it all fixed, including the stickers and whatever. And then I started working on the library. Actually, Ven started about 1.5 years ago to work on the test harness. And I used much of his logic on how to access it, because there's like it uses an Arduino to access the RAM and so on, and it needed some assembly to actually get the timing correct. And so I used this to create then a library and a shield for this. Again, it's on my table over there. With that, you can easily create extensions. So the reason for why I've done this is I want to make sure that the barrier of entry to create your own extensions to the Model 1 is the lowest as possible. Arduino, a lot of people can do Arduino. It makes it easy. And so I created this library to make it easy to access it. So for example, if you're not familiar with code, so in the setup is what you have to do as soon as the machine starts up, the Arduino. And so what you always do is begin on that to just activate it. And then you do activate the test signal, so now you can take over the machine, right? Because now you are the CPU as the Arduino. So you can take over the machine, and now you can read and write to the memory as you want. To make it a lot easier, I also put some additional things like ROM, where you can get a checksum, or you can identify the ROMs you have installed. For a cassette, you can, because Tandy abused the cassette interface also for the character mode for 64 and 32. You can actually switch this now. Previously, you always have to reset the computer. Here, you can actually switch it. You can deactivate the remote. You can even create sounds with this. You can send sounds out of the cassette interface or read even sounds there. So all of this is already implemented. Same for the keyboard, same for the video. So you can even do a print, you can scroll and everything. So all of this to make it a lot easier to develop extensions. So if you're interested, talk to me. I have a couple of these shields available. And if you look at the case, you see there are a lot of buttons. There's a buzzer. There's actually an SD card reader, so you can have a SD card, maybe programs on it, which you inject. And so with that, you can also access the LEDs. You can ask the joystick direction and so on. Again, everything to make it easy if you want to build extension for the Model 1. And one example here I built, which somehow doesn't work today, and I have to figure out why, is the test harness. Again, Ven started this 1.5 years ago. We worked together on reshaping this a little bit, and we are close to finishing it. But here, for example, you can see it's a keyboard tester. So you press the keys, and you can actually see what it is. It has an oscilloscope in it. It has a mirror where you can actually show on this little screen what should be on the Model 1. So there you can see, okay, is the video RAM working, or is just the video section broken, right? And so you can test multiple things with that. It has multiple features. Let me see the time, yeah. The problem with that is there is a flaw in, my opinion, there's a flaw in the Model 1. And I talked about the test signal, right? The test signal disconnects everything, right? When you trigger it, it just disconnects the CPU from the rest of the system. The problem is that it might still execute something. You can see that it disconnects it instantly, but it might actually is in a process to read a memory address. If it does this, it sends out a read address. It puts the address on the bus, which then goes out to all of the additional components, and then the test signal comes in. It disconnects everything, and with the blue you can see it's now random because it's floating. It has some value, but now it reads some address in the RAM and returns that value to the CPU, and now it crashes. The same thing is for the video RAM, right? For the writing. If you write to it, you maybe write it to a random place in memory, and this crashes to about 30% of the time when you start turning on the test signal. So that means probably the screen printer, for example, which uses the test signal to access the video memory, should crash the computer once in a while. I don't know exactly because I haven't seen one, but you can see here where the system incorrectly wrote something into the video RAM. The fix is to use the bus acknowledge signal. With the bus acknowledge signal is there to finally signal, okay, I'm done with all of this. Now you can take over. But the Model 1 doesn't actually check for this. What you can do is you can cut this connection and connect the bus acknowledge for this. And the same thing you do for the CPU gating. And this is actually a pretty quite small fix. You just make the trace cut here in the orange. You can see the red, these are the bus request and bus acknowledge pins, and you just create a jumper. And that will fix it. That will make sure that your Model 1 doesn't crash anymore in this case. Yeah, and that's all. Any questions? I know it was a lot. Yes?
Yeah, I have a couple of thoughts.
Sure.
One is, when you had found all the duplicate reference designators, KiCad won't let you have duplicates. How did you get past that? Did you just like massage the silk screens and stuff to
Yeah, so I changed the silk screen to make sure it has the right. I mean,
Schematics are incorrect.
but the schematics I had C_C for corrected. I needed to add a different designator to it, so I have a C_, and there's also the C_R for the duplicate resistor to make sure that there's no conflict.
And then the thought on the test signal,
Yeah.
DRAM refresh, maybe
Yes.
USY, it also could be crashed.
No, the Arduino library does a refresh as well.
It does do the refresh.
Yes, it actually there's the Model 1 has like a 82 or 90 something like microsecond refresh, while the Arduino has a 78, I believe. So it does actually a little faster even.
The other thought on the bus acknowledge grant is after you do the bus request for the test, wait a longer period of time such that you know the CPU flushes out the signal.
Yes, I actually tried that. I have to remember what it was. There was another issue for this. I can't recall right now what it was, but I tried multiple things. I tried the wait signal. I tried the.
No, not wait. I'm just
Yeah.
when you get the request, wait.
We actually did that too.
500 nanoseconds rather than
We actually did that too. Ben, do you remember what it was? Okay. There were. I tried that too. Let me think about it, and I can get back to you. Yeah, but there was another issue there. Any other questions? Yeah.
With everything you've learned, sort of what's next? Is there thoughts of like what would be a modern revision to all the things, the oddities and so on, or is there other
Yeah.
hardware that you're looking to replicate?
So yeah, that was actually my initial thought, to create now a modern version with all of these fixed. But there is now a version out there. There is the K revision, which is actually pretty good. And I was like, okay, I don't need to do anything anymore because it's there. And so if you want to have a modern version, this is actually a pretty good one. It uses the Japanese version, so it has also PAL and everything. So it has all the advantages already built in. But what I'm looking for right now is I'm working on a replica of the expansion interface. I have 2 revisions already of the expansion interface, working on that. And then I have 2 more from LNW80 expansion interfaces. I've gotten today also Model 3. So yeah, I have a couple of projects ahead of me. Any other? Yes?
How long do you think you got into this project? How many hours?
Oh. Too much. I started about 2 years ago with the Model 1. Before that, I actually didn't even know about the Model 1. Yeah, 2 years ago I started with it. But yeah, all of this again is all open source and available. And if you have questions on building these things, let me know. Any other questions? Okay, thank you.